You know, according to de Broglie hypothesis, material particles in motion have a wave associated with it. In fact, the wave or wave packet which is associated with a material particle is actually known as the pilot wave. De Broglie has given the idea that material particle will be associated with wave, but he has not proposed a wave equation for such a wave. But you know, every wave is represented by a particular differential equation which is called wave equation. In fact, it was Schrodinger who proposed the wave equation for matter wave in 1926. And you also know that every wave is characterized by a particular quantity which is called actually wave function. So Schrodinger equation also discussed or also proposed a wave function for the matter wave, and this wave function is actually of abstract nature, and we simply denote it by the symbol psi. So you can say the quantity that characterizes the de Broglie wave. De Broglie wave is called wave function. Wave function, and it is denoted by psi, or you may call Ket psi. In Dirac notation, it is also denoted by Ket psi. In fact, as I have told you, this psi is of abstract nature and it may be a complex function. It may be a complex function. So, to get the wave equation for matter wave, let us assume a simple plane wave in x direction, and starting from it we will arrive at a particular result which will represent the time dependent form of Schrodinger equation. Actually, Schrodinger equation has two forms, time dependent form and time independent form. And in this first lecture on Schrodinger equation, I will just give you the concept of the time dependent form of Schrodinger equation. So let us first of all represent such a wave as a plane wave. So let us assume psi as a plane wave. In x direction, and you know what will be the plane wave if we consider the one-dimensional situation, that is in x direction. You know this is written as psi of xt is equal to a constant a e to the power kx minus omega t. You know it. In fact, in this equation, you know what is this k. Actually, k is the wave vector, or you can say it is propagation constant, or it is angular wave number. So where k equal to 2 pi over lambda, and this is wave vector, and lambda is what? Lambda is the wavelength of the wave. Wavelength of the wave. And this omega is what? This is actually the cyclic frequency or the angular frequency of the wave. This is cyclic frequency of the wave. Now, if we assume that E be the total energy and P the momentum of the particle, because we are considering here the matter wave, so definitely there will be a particle in motion. And one thing you must remember that Schrodinger equation is actually a non-relativistic equation. So in this case, motion of the particle must be non-relativistic, that its speed should be much smaller than c. So in this condition, we consider that E equal to total energy of the particle. Total energy of the particle, and P equal to momentum of the particle. Momentum of the particle. Then, as you know, according to de Broglie concept, we can always take a photon analogy, and we take E is simply equal to energy of a photon, because according to de Broglie hypothesis, any formula which is applicable for photon, that can be used for any material particle. So you can write that E is equal to h cross omega. And you also know, according to de Broglie hypothesis, this lambda is equal to h over p. H over p. And as you know, h can be written as 2 pi h bar over p. 2 pi h bar over p. And this 2 pi h bar over p, this is in fact lambda, and this, if you want to write the expression for k, then what will be k? K is equal to 2 pi over lambda, and lambda has been defined in this manner, so you can see this is 2 pi over 2 pi h bar over p. So p will be here now, and this 2 pi and 2 pi will cancel, and this k will be simply equal to p over h bar. And from in this relation, you can see omega can be written as E over h bar. So now let us substitute at the place of k, p over h bar, and at the place of omega we will write E over h cross. So making these two substitutions, what will be the expression for the plane wave psi of xt, you can see k and omega will be replaced by p by h bar and e by h bar. So equation 1 can be written as psi of xt equal to a e to the power I over h cross you can see this k is p by h cross. I have taken this h cross as a common factor, so this will be xp minus et, and let us say this is equation 2. As you can see here, we have introduced this k from this relation, which is actually the de Broglie formula. So now this plane wave is not in general a plane wave, but it represents a matter wave, because you have used the de Broglie formula for the wavelength of matter wave. So now equation 2 represents actually the plane wave for the matter wave. So this wave description of the wave equivalent is equivalent of an unrestricted particle of total energy E and momentum P moving in positive x direction. Now we will make some of the mathematical steps to get the actual proper Schrodinger equation, which is actually Schrodinger's time dependent equation. And for this, as you can see here, that psi is a function of two variables x and t. So first of all, we will differentiate partially this equation 2 times with respect to x. So now you will see del psi by del x will be what? As you are differentiating with respect to x partially, so we will take this t as a constant factor. So in this condition, this will be what? This is I over h bar p a e to the power I over h bar xp minus et. We will again differentiate it with respect to x partially. So now again this factor p times I by h bar will be outside. So you can say that del 2 psi by del x square will be now what? I see here ip over h bar whole square a e to the power I by h bar xp minus et, and you know this I square will be minus 1, so this can be simply written as minus p square over h bar square, and you can see this factor a e to the power I over h bar xp minus et, this is nothing, it is simply psi. So we can write that del 2 psi del x square is equal to this much. So we have obtained del 2 psi by del x square. Why we are obtaining this? Because you know the classical wave equation actually contains the second order partial derivative with respect to a space coordinate, and also a first order derivative of psi with respect to time t. So we are obtaining such partial derivatives. Now we will again differentiate this equation 2 partially with respect to t. When you will differentiate it partially with respect to t, you will take this x as a constant factor. So keeping x constant, we will differentiate psi with respect to t. So again, what will be del psi by del t? You can see here. Del psi by del t. This will be actually equal to, as you can see here, as this equation, this will be in fact minus e times I over h bar a e to the power I h bar xp minus et. So now this will be minus I over h bar e a e to the power I over h bar xp minus et. xp minus et. Again, you can write psi instead of this underlined expression. So you can see that del psi by del t is equal to minus IE over h bar psi. Now, as I have told you earlier that the Schrodinger equation is based upon the assumption that motion of the particle is non-relativistic. It means we will assume that the particle is moving with a speed v which is much smaller than speed of light in free space, and in this non-relativistic situation the total energy of the particle is actually the sum of the kinetic energy and potential energy of the particle. So you can say as the motion of the particle is non-relativistic, that is, we assume that v is much smaller than c. So the total energy of the particle E is equal to kinetic energy of the particle plus potential energy of the particle, and we denote this kinetic energy by the symbol T and potential energy by V. And you know the non-relativistic expression for kinetic energy is what? This is half mv square, or in terms of momentum you write it p square over 2m. So in this condition you can write E is equal to p square over 2m plus v of x, or so you can write simply v, and say this is equation number what? This is equation number 3, let us say. So this is the total energy of the particle when we assume that its motion is non-relativistic, that is its speed is much smaller than c. Now we will multiply this equation 3 both sides by psi. So multiplying both sides of equation 3 by psi, we get what you will get. You can see here this will be simply E psi equal to P square over 2m psi plus V psi. Say this is equation 4. Now you have seen earlier that what is del 2 psi by del x square and what is del psi by del t, just you have seen here. So you can see what we have obtained in this calculation. Del 2 psi by del x square is equal to this much and del psi by del t is equal to this much. Actually, from this expression we will find the expression for E psi and also for P square psi. So you can see from here this P square psi will be what? This P square psi will be equal to P square psi will be equal to, you can see from here, this will be minus h cross square del 2 psi by del x square. And from here you can see what will be the value of E psi. In fact, this E psi will be equal to minus h cross over I del psi by del t. So we will now make this substitution, that is P square psi and E psi, in this equation, where in this equation number 4. So after substituting for E psi and P square psi, what you have obtained earlier, we get. What you will get, you can see easily. E psi, you know, you have obtained just now, that this is equal to minus h bar over I del psi by del t, del psi by del t. And P square psi, you have obtained that this is actually equal to minus h bar square del 2 psi by del x square, and here is over 2m, so we write 2m here, and del 2 psi by del x square and plus V psi. Now you know that 1 over I is equal to minus I. So when you will write 1 over I equal to minus I, then what will be the LHS? You can see this will be simply IH bar del psi by del t, and this is equal to minus h bar square over 2m del 2 psi by del x square plus V psi. Actually, this is the time dependent Schrodinger equation in one dimension. You can see here. This equation 5 is nothing. This is simply the time dependent form of Schrodinger equation in one dimension. So you can write this is the time dependent form of Schrodinger equation. Schrodinger equation. Now, from this one-dimensional equation, we can write the equation in 3 dimensions, taking the fact into this equation. So, in 3 dimensions, in 3D, the time dependent equation is written as you can see this will be IH bar del psi by del t equal to minus H bar square over 2m. Now in one-dimensional form you can see here is del 2 psi by del x square, but if you consider that your space is 3-dimensional, then psi will be a function of x, y and z. So we will also take the second order derivative with respect to y and z here. So in this condition you can write this is del 2 psi by del x square plus del 2 psi by del y square plus del 2 psi by del z square plus v psi. And now you can write this IH bar del psi by del t, and this equal to minus h bar square over 2m, and you can see the expression inside this bracket. This is simply del square psi, where del square you know is Laplacian, and this Laplacian is actually del 2 by del x square plus del 2 by del y square plus del 2 by del z square and plus v psi. Here this operator del square is known as Laplacian operator. As you know, this is Laplacian, and so you can write IH bar del psi by del t, and this equal to minus h bar square over 2m del square plus v of r. Now we will write position vector r and psi. So this is actually the time dependent form of Schrodinger equation in 3 dimensions. Now this operator which is inside this square bracket is actually the Hamiltonian operator, and IH bar del del t operator is known as energy operator or total energy operator. So in terms of the total energy and the Hamiltonian operator, we can write this equation in a very compact form. Actually equation number will be 6 here. This is equation 6, and this equation 6, as I have told you, represents the Schrodinger time dependent equation in 3D. So now you can see the operator IH bar del del t. This actually represents the total energy E, and the operator minus h bar square over 2m del square plus this v is actually H, which is Hamiltonian of our system. This is Hamiltonian. And therefore, in compact form, you may write this equation in this manner. This is E psi equal to H psi. In fact, we also write this Schrodinger equation in Ket notation proposed by Dirac. So in Ket notation, we can write in Ket notation, you can write E Ket psi equal to H Ket psi, or you can also write in this way. This is I H cross del T Ket psi equal to minus H cross square over 2m plus V Ket psi. This is actually the Schrodinger time-dependent equation in 3 dimensions in Ket notation. So this is Schrodinger's time-dependent equation. One should here must be noted that the Schrodinger equation is valid only when we consider the non-relativistic motion of the material particle, and also we do not take into account the spin of the particle. So this equation is valid only for a spinless particle, because spin was not introduced in this Schrodinger wave equation. But for a spinless particle, this equation is in fact well behaved, and it is very applicable in solving the quantum mechanical problem. So there are 2 limitations. First one is motion should be non-relativistic. Motion should be non-relativistic. And number 2, a spin should not be taken into account. Now in the next lecture, we will see that time independent form or steady state form of Schrodinger equation.